Welcome to the Nerdjacker's Vault. Today we are reading On the Sphere and Cylinder by Greek mathematician and physicist Archimedes, translated by T.L. Heath and Said Mahdi Hassan. Translator's note: this is a working translation of Archimedes' On the Sphere and Cylinder. The original text and the translation by T.L. Heath is written in a highly technical proposition-by-proposition style, with dense proofs that can be difficult to follow when read aloud. In this version, the core ideas, major results, and logical flow are preserved, while the language is adapted for clarity and natural listening. Repetitive steps are streamlined where they do not add new understanding, and geometric constructions are described in words to maintain accessibility. The mathematical rigor and Archimedes' remarkable insights remain intact. This is not a literal word-for-word rendering, nor a modern commentary, but a translation intended to let the beauty and power of the original ideas reach a broader audience. Book 1. Archimedes to Dositheus greeting. On a former occasion I sent you the investigations which I had up to that time completed, including the proofs showing that any segment bounded by a straight line and a section of a right-angled cone, a parabola, is 4/3 of the triangle which has the same base with the segment and equal height. Since then certain theorems not hitherto demonstrated have occurred to me, and I have worked out the proofs of them. They are these. First, that the surface of any sphere is 4 times its greatest circle. Next, that the surface of any segment of a sphere is equal to a circle whose radius is equal to the straight line drawn from the vertex of the segment to the circumference of the circle, which is the base of the segment. And further, that any cylinder having its base equal to the greatest circle of those in the sphere, and height equal to the diameter of the sphere, is itself in content half as large again as the sphere, and its surface also including its bases is half as large again as the surface of the sphere. Now these properties were all along naturally inherent in the figures referred to, but remained unknown to those who were before my time engaged in the study of geometry. Having, however, now discovered that the properties are true of these figures, I cannot feel any hesitation in setting them side by side, both with my former investigations and with those of the theorems of Eudoxus on solids, which are held to be most irrefragably established, namely, that any pyramid is 1/3 part of the prism, which has the same base with the pyramid and equal height, and that any cone is 1/3 part of the cylinder, which has the same base with the cone and equal height. For though these properties also were naturally inherent in the figures all along, yet they were in fact unknown to all the many able geometers who lived before Eudoxus, and had not been observed by anyone. Now, however, it will be open to those who possess the requisite ability to examine these discoveries of mine. They ought to have been published while Conon was still alive, for I should conceive that he would best have been able to grasp them and to pronounce upon them the appropriate verdict. But, as I judge it well to communicate them to those who are conversant with mathematics, I send them to you with the proofs written out, which it will be open to mathematicians to examine. Farewell. I first set out the axioms and the assumptions which I have used for the proofs of my propositions. First, we need to set some definitions. 1. There are in a plane certain terminated bent lines, which either lie wholly on the same side of the straight lines joining their extremities, or have no part of them on the other side. Imagine drawing a curve between 2 points on a sheet of paper, something like an arc, or even the outline of a hill. There are, in a plane, certain bounded curved lines whose endpoints can be joined by a straight line, such that the entire curve lies on one side of that line and never crosses to the other. Now draw a straight line connecting those same 2 endpoints. If your curve stays entirely on one side of that straight line, never dipping below it or crossing through it, then it belongs to the kind of line being described here. Of 2. I apply the term concave in the same direction to a line such that, if any 2 points on it are taken, either all the straight lines connecting the points fall on the same side of the line, or some fall on one and the same side, while others fall on the line itself, but none on the other side. Imagine a curve that bends in a single, consistent direction, like the inside edge of a bowl. Pick any 2 points on that curve. Now draw a straight line between them. If every such line you draw either stays on the same side of the curve, or sometimes lies directly on the curve itself, but never crosses to the other side, then the curve is said to be concave in the same direction. This keeps the structure intact, but lets the idea settle through a simple repeated action. Pick 2 points, draw a line, observe what never happens. 3. Similarly also there are certain terminated surfaces, not themselves being in a plane but having their extremities in a plane, and such that they will either be wholly on the same side of the plane containing their extremities, or have no part of them on the other side. Now imagine something similar, but no longer flat on the page. Think of a surface, something like a curved sheet or the skin of a dome. Its edges still lie along a flat plane, like a rim resting on a table, but the surface itself rises above it. If that surface stays entirely on one side of the plane that contains its boundary, or at least never passes through to the other side, then it belongs to the kind of surface being described here. This keeps the same idea, just lifted from lines into surfaces, like moving from a drawn curve to something you could almost reach out and touch. 4. I apply the term concave in the same direction to surfaces such that, if any 2 points on them are taken, the straight lines connecting the points either all fall on the same side of the surface, or some fall on one and the same side of it, while some fall upon it, but none on the other side. Imagine something like a curved sheet, a dome, or the inside of a bowl. Pick any 2 points on that surface and draw a straight line connecting them. If every such line either stays on the same side of the surface, or sometimes lies directly on it, but never passes through to the other side, then the surface is said to be concave in the same direction. It's the same quiet test again. Choose 2 points, draw a line, and notice what never happens. 5. I use the term solid sector when a cone cuts a sphere and has its apex at the center of the sphere to denote the figure comprehended by the surface of the cone and the surface of the sphere included within the cone. Now imagine a sphere, like a perfectly round ball. From its very center, a cone begins to extend outward, spreading until it cuts through the surface of the sphere. The tip of the cone stays fixed at the center, while its sides open up and meet the sphere's surface. What you're left with is a portion of the sphere, enclosed within the cone, bounded partly by the curved surface of the sphere, and partly by the sides of the cone. This shape is what is called a solid sector. It's less a new object, and more a way of isolating a part of something familiar, like carving out a piece of the sphere using straight edges that all point back to its center. 6. I apply the term solid rhombus when 2 cones with the same base have their apices on opposite sides of the plane of the base in such a position that their axes lie in a straight line, to denote the solid figure made up of both the cones. Imagine a cone standing upright on a circular base. Now place another cone on that same base, but flipped, so its tip points in the opposite direction. The 2 cones meet at the base, their tips extending away from each other, perfectly aligned along a single straight line. What you get is a single solid formed from both cones joined together at their base. This figure is what is called a solid rhombus. It's a kind of symmetry, 2 identical shapes facing away from each other, balanced along a common axis, as if mirrored through the plane between them. Our assumptions are: 1. Of all lines which have the same extremities, the straight line is the least. Take 2 points on a page. There are many ways to connect them. You could draw a curve, an arc, something that bends or loops before reaching the other side. But among all these possible paths, there is one that stands apart. If you draw a straight line between the 2 points, that path will always be the shortest. It's a simple idea, almost something you accept without thinking. But here it becomes a foundation, quietly setting the standard for what it means to take the most direct route between 2 places. 2. Of other lines in a plane and having the same extremities, any 2 such are unequal whenever both are concave in the same direction, and one of them is either wholly included between the other and the straight line which has the same extremities with it, or is partly included by and is partly common with the other, and that line which is included is the lesser of the 2. Take 2 curves that share the same endpoints, both bending in the same direction. At first glance, they might look similar, just different ways of arching between the same 2 points. But there's a subtle difference you can look for. If one of the curves sits entirely between the other curve and the straight line connecting their endpoints, or even if part of it overlaps while the rest stays tucked inside, then the relationship becomes clear. The curve that stays inside, closer to the straight line, is always the shorter of the 2. It's almost like comparing 2 paths along a hillside. One rises higher, stretching outward. The other stays lower, closer to the direct route. And even without measuring, you can begin to sense which one must be shorter. 3. Similarly, of surfaces which have the same extremities, if those extremities are in a plane, the plane is the least in area. Now imagine a boundary that lies flat on a plane, like a loop drawn on a sheet of paper. There are many surfaces that could span this boundary. You could stretch something curved over it, like a thin dome, or let it rise and dip in different ways. But among all possible surfaces that share the same edge, one stands apart. If the surface lies completely flat in the plane of its boundary, it will always have the least area. It's the surface equivalent of a straight line, nothing extra, nothing lifted or curved, just the most direct way of filling the space within a given edge. 4. Of other surfaces with the same extremities, the extremities being in a plane, any 2 such are unequal whenever both are concave in the same direction, and one surface is either wholly included between the other and the plane which has the same extremities with it, or is partly included by and partly common with the other, and that surface which is included is the lesser of the 2 in area. Now take that same idea and lift it from lines to surfaces. Imagine 2 surfaces that share the same boundary, with that boundary lying flat in a plane. Both surfaces bend in the same general direction, like 2 different domes stretched over the same edge. If one of these surfaces stays entirely between the other and the flat plane beneath, or even if part of it overlaps while the rest remains tucked inside, then a pattern begins to emerge. The surface that stays inside, closer to the plane, will always have the smaller area. It's a quiet comparison, but a consistent one. The more a surface rises away, the more it stretches, and the one that holds closer to the plane remains the lesser of the 2. Further, of unequal lines, unequal surfaces, and unequal solids, the greater exceeds the less by such a magnitude as, when added to itself, can be made to exceed any assigned magnitude among those which are comparable with it and with one another. These things being premised, if a polygon he inscribed in a circle, it is plain that the perimeter of the inscribed polygon is less than the circumference of the circle. For each of the sides of the polygon is less than that part of the circumference of the circle which is cut off by it. This one has 2 movements in it, and it's easy to lose people if they blur together. So the key is to let the first idea settle before gently moving into the circle. First, think about comparing things that are unequal, lines, surfaces, or even solid shapes. If one is greater than another, then the difference between them is not something small or fixed. It's something you can keep adding to itself, again and again, until eventually it becomes larger than any size you choose to compare it with. Now, with that in mind, return to something more familiar, a circle. Imagine drawing a polygon inside it, its corners touching the circle, its sides cutting across the interior. Each side of the polygon replaces a small arc of the circle's edge, but instead of following the curve, it cuts straight across. And because of that, each side is just a little shorter than the arc it replaces. So when you follow the entire boundary of the polygon, adding up all its sides, it will always fall short of the full circumference of the circle. It's a quiet beginning, but an important one. A way of saying, even when you get close to the circle by using straight lines, you never quite reach it. Proposition 1. If a polygon he circumscribed about a circle, the perimeter of the circumscribed polygon is greater than the perimeter of the circle. Imagine a circle, and around it a shape made of straight lines, each side just touching the circle, holding it in place, almost like a loose frame. At first, it feels like the shape is following the circle. It surrounds it, stays close to it. But if you look carefully, it never really matches it. Each straight side cuts across what would otherwise be a gentle curve. It stretches a little farther than the part of the circle it touches, just enough to stand outside it. And that small difference happens again and again, side after side. So when you walk along the entire boundary of that outer shape, you end up traveling a longer path than if you had simply followed the circle itself. It's the same idea from before, just seen from the other side. One shape tries to trace the circle from within and always falls short. The other wraps around it from the outside and always goes a little too far. And the circle stays somewhere in between. Proposition 2. Given two unequal magnitudes, it is possible to find two unequal straight lines, such that the greater straight line has to the less a ratio less than the greater magnitude has to the less. Start with two things that are clearly unequal, one larger, one smaller. Now, instead of comparing them directly, imagine trying to recreate that same kind of difference using straight lines. At first, you might think you have to match the comparison exactly, but that's not the point here. What this tells us is you can always find two straight lines, still unequal, where the difference between them feels less extreme than the original pair. It's like adjusting a comparison until it becomes gentler. No matter how large the gap you begin with, you can step it down, find another pair where the larger still exceeds the smaller, but not by as much. You're not matching the original comparison, you're reducing it. The inequality remains, but the proportion between them becomes less. Proposition 3. Given two unequal magnitudes in a circle, it is possible to inscribe a polygon in the circle and to describe another about it so that the side of the circumscribed polygon may have to the side of the inscribed polygon a ratio less than that of the greater magnitude to the less. Start with two unequal magnitudes and a circle. It is always possible to draw one polygon inside the circle and another around it so that both share the same number of sides, each side of the inner polygon touching the circle from within, and each side of the outer polygon touching it from without. Now compare a single side of the outer polygon with the corresponding side of the inner one. By increasing the number of sides, both polygons begin to follow the circle more closely. The sides become shorter, and the difference between them becomes smaller. In this way, you can make the ratio between a side of the outer polygon and a side of the inner polygon less than the ratio of the given magnitudes. The shapes remain unequal, but their difference can be reduced as much as required, while still enclosing the same circle. Proposition 4. Again, given two unequal magnitudes in a sector, it is possible to describe a polygon about the sector and to inscribe another in it, so that the side of the circumscribed polygon may have to the side of the inscribed polygon a ratio less than the greater magnitude has to the less. The inscribed polygon, found in this proposition, is one which has for two sides the two radii bounding the sector, while the remaining sides, the number of which is by construction, some power of 2, subtend equal parts of the arc of the sector. The circumscribed polygon is formed by the tangents parallel to the sides of the inscribed polygon and by the two bounding radii produced. Start with two unequal magnitudes, and now consider not a full circle, but a sector, a portion of a circle bounded by two radii and the arc between them. It is possible to draw one polygon inside this sector and another around it, both shaped in relation to the same boundaries. The inner polygon begins at the center, using the two radii as part of its sides. The remaining sides step along the arc, dividing it into equal parts, so that the shape fits neatly within the sector. The outer polygon is formed differently. Its sides do not follow the arc but stand outside it, touching it by means of lines drawn parallel to the sides of the inner polygon, while the two radii are extended outward to meet them. Now compare a side from the outer polygon with the corresponding side from the inner one. As before, by increasing the number of divisions along the arc, both shapes begin to follow the sector more closely. Their sides become smaller, and the difference between them is reduced. In this way, the ratio between a side of the outer polygon and a side of the inner polygon can be made less than the ratio of the given magnitudes. Even within just a part of a circle, the same pattern holds. The inner shape falls short, the outer extends beyond, and between them, the gap can be made as small as needed. Proposition 5. Given a circle and two unequal magnitudes, to describe a polygon about the circle and inscribe another in it, so that the circumscribed polygon may have to the inscribed a ratio less than the greater magnitude has to the less. Start with a circle and two unequal magnitudes. It is possible to draw a polygon around the circle and another within it, so that both have the same number of sides, each side of the inner polygon touching the circle from within, and each side of the outer polygon touching it from without. Now compare the whole boundary of the outer polygon with that of the inner one. By increasing the number of sides, both polygons come closer to the circle. The inner polygon fills more of it, while the outer one tightens around it. As this happens, the difference between their perimeters becomes smaller. In this way, the ratio of the circumscribed polygon to the inscribed polygon can be made less than the ratio of the given magnitudes. Proposition 6. Similarly, we can show that, given two unequal magnitudes in a sector, it is possible to circumscribe a polygon about the sector and inscribe in it another similar one, so that the circumscribed may have to the inscribed a ratio less than the greater magnitude has to the less. And it is likewise clear that, if a circle or a sector, as well as a certain area, be given, it is possible, by inscribing regular polygons in the circle or sector, and by continually inscribing such in the remaining segments, to leave segments of the circle or sector which are together less than the given area. For this is proved in the Elements by Euclid, but it is yet to be proved that, given a circle or sector and an area, it is possible to describe a polygon about the circle or sector, such that the area remaining between the circumference and the circumscribed figure is less than the given area. Start again with two unequal magnitudes and a sector. Just as with the full circle, it is possible to draw a polygon around the sector and another within it, both shaped to fit the same boundaries, and by choosing them carefully, the ratio of the outer figure to the inner one can be made less than the ratio of the given magnitudes. There is another idea that follows from this. Take a circle, or even just a sector, and imagine filling it with polygons. First one is drawn inside it. Then, in the spaces that remain, more polygons are added, and then again in the smaller gaps that are left. Each step reduces what is left uncovered. If this process continues, the remaining pieces, the small curved segments between the polygon and the boundary, can be made together smaller than any given area. This much has already been established, but there is still something left to show. Not only can we fill the inside more and more closely, we can also approach from the outside. Given a circle or a sector and a certain area, it is possible to draw a polygon around it so closely that the space left between the polygon and the curve is less than that given area. So whether from within or from without, the gap can always be reduced until what remains is smaller than any chosen measure. Proposition 7. If in an isosceles cone, a right circular cone, a pyramid be inscribed having an equilateral base, the surface of the pyramid, excluding the base, is equal to a triangle having its base equal to the perimeter of the base of the pyramid, and its height equal to the perpendicular drawn from the apex on one side of the base. Since the sides of the base of the pyramid are equal, it follows that the perpendiculars from the apex to all the sides of the base are equal, and the proof of the proposition is obvious. Imagine a cone, smooth, circular, rising to a single point. Now, inside it, place a pyramid whose base is an equilateral triangle, sitting flat on the base of the cone, and whose apex meets the tip of the cone. The pyramid fits neatly within the cone, its three sides rising evenly to the top. Now focus only on the sides of the pyramid, not the base, but the three triangular faces that meet at the apex. If you were to unfold these faces and lay them flat, something simple appears. They together form a single triangle whose base is equal to the full perimeter of the pyramid's base, and whose height is the same as the perpendicular drawn from the apex down to any side of that base. Because the base is equilateral, each side is the same, and from the apex, the distance to each side is also the same, so each face of the pyramid matches the others, and they combine cleanly into this one triangle. What looks like three separate surfaces, when gathered together, behave like one. Proposition 8. If a pyramid be circumscribed about an isosceles cone, the surface of the pyramid, excluding its base, is equal to a triangle having its base equal to the pelvimeter of the base of the pyramid, and its height equal to the side a generator of the cone. Now imagine the reverse situation. Instead of placing a pyramid inside a cone, draw one around it, so that the pyramid encloses the cone and touches it along its sides, while both share the same base. Again, set aside the base of the pyramid and look only at its outer faces, the triangular sides rising to the apex. Taken together, these faces are equal in area to a single triangle whose base is equal to the perimeter of the pyramid's base, and whose height is equal to the slant side of the cone. So once again, several surfaces can be gathered into one simpler figure. The sides of the pyramid, though separate in shape, combine as if they were a single triangle stretched out along the full boundary below. The base of the pyramid is a polygon circumscribed about the circular base of the cone, and the line joining the apex of the cone or pyramid to the point of contact of any side of the polygon is perpendicular to that side. Also, all these perpendiculars, being generators of the cone, are equal, whence the proposition follows immediately. Proposition 9. If in the circular base of an isosceles cone a chord he placed, and from its extremities straight lines he drawn to the apex of the cone, the triangle so formed will he less than the portion of the surface of the cone intercepted between the lines drawn to the apex. Take a cone and look at its circular base. Now choose a chord in that base, a straight line joining 2 points on the circle, but not passing through the center unless it happens to. From each end of that chord, draw a straight line up to the apex of the cone. These 3 lines, the chord below and the 2 lines rising to the apex, form a triangle. But this triangle does not match the curved portion of the cone lying above it. It cuts across it. And because it cuts straight across, the triangle is less than the portion of the cone's surface enclosed between those 2 lines. So even when the same boundary is used, the flat figure remains smaller than the curved surface that stretches between those edges. Proposition 10. If in the plane of the circular base of an isosceles cone, two tangents he drawn to the circle meeting in a point, and the points of contact and the point of concourse of the tangents be respectively joined to the apex of the cone, the sum of the two triangles formed by the joining lines and the two tangents are together greater tighten the included portion of the surface of the cone. Now imagine the cone again, but this time do not begin from a chord inside the circle. Instead, draw two tangents to the circular base, two straight lines that touch the circle from outside and meet at a single point. Then join that meeting point to the apex of the cone, and also join each point where the tangents touch the circle to the apex. This gives you two triangles, side by side, rising from the tangents up to the tip of the cone. Now compare those two flat triangles with the curved portion of the cone's surface lying between the same bounding lines. The two triangles together are greater than that included part of the cone. So here the comparison goes the other way from before. When the boundary is taken outside the circle by tangents, the flat figures no longer fall short, they exceed the curved surface they enclose. Proposition 11. If a plane parallel to the axis of a right cylinder cut the cylinder, the part of the surface of the cylinder cut off by the plane is greater than the area of the parallelogram in which the plane cuts it. Imagine a right cylinder, and then slice it with a plane running parallel to its axis. That plane cuts out a four-sided figure, a parallelogram, where it passes through the cylinder. At the same time, it also cuts off a curved portion of the cylinder's outer surface. Now these two figures are bounded by the same height and reach across the same opening, but they are not equal. The curved surface of the cylinder is greater than the parallelogram formed in the cutting plane. So once again, a flat figure drawn across the space falls short of the curved surface that bends around it. Proposition 12. If at the extremities of two generators of any right cylinder tangents he drawn to the circular bases in the planes of those bases respectively, and if the pairs of tangents meet, the parallelograms formed by each generator and the two corresponding tangents respectively are together greater than the included portion of the surface of the cylinder between the two generators. The proofs of these two propositions follow exactly the methods of propositions 9, 10, respectively, and it is therefore unnecessary to reproduce them. From the properties thus proved, it is clear that, if a pyramid be inscribed in an isosceles cone, the surface of the pyramid excluding the base is less than the surface of the cone excluding the base, and that, if a pyramid be circumscribed about an isosceles cone, the surface of the pyramid excluding the base is greater than the surface of the cone excluding the base. It is also clear from what has been proved both that, if a prism be inscribed in a right cylinder, the surface of the prism made up of its parallelograms excluding its bases is less than the surface of the cylinder excluding its bases, and that, if a prism be circumscribed about a right cylinder, the surface of the prism made up of its parallelograms is greater than the surface of the cylinder excluding its bases. Take a right cylinder and focus on two of its generators, two straight lines running along its side from one base to the other. At the top and bottom of these lines, draw tangents to the circular bases. Each pair of tangents meets, forming straight edges outside the cylinder. Now, using each generator and its two corresponding tangents, you get two parallelograms, one at the top, one at the bottom, each stretching between the lines you've drawn. Compare these flat parallelograms with the curved portion of the cylinder's surface that lies between the same two generators. Together, the parallelograms are greater than that part of the cylinder's surface. This follows the same pattern seen before. When a flat figure is drawn inside a curved surface, it falls short. When it is formed outside, using tangents, it extends beyond. And from these comparisons, a broader picture begins to settle. If a pyramid is placed inside a cone, its side surfaces are less than the surface of the cone. If it is drawn around the cone, its sides are greater. In the same way, a prism inside a cylinder falls short of the cylinder's surface, while one drawn around it exceeds it. So whether with cones or cylinders, the pattern holds steady. From within, the straight-edged figure remains smaller. From without, it becomes larger, and the curved surface stays between them. Proposition 13. The surface of any right cylinder excluding the bases is equal to a circle whose radius is a mean proportional between the side that is a generator of the cylinder and the diameter of its base. Consider a right cylinder and focus only on its curved surface, the part that wraps around, leaving out the top and bottom. This surface can be matched to something simpler. It is equal in area to a circle, but not the original base. Instead, this new circle has a radius chosen in a particular way. It lies between two lengths already present, the height of the cylinder, its generator, and the diameter of its base. More precisely, the radius of this circle is a mean proportional between those two. That is, it stands in the same ratio to the height as the height does to the diameter. So the curved surface of the cylinder, though spread out and wrapped around, can be gathered into a single flat figure, a circle, whose size is determined by balancing these two lengths. Proposition 14. The surface of any isosceles cone excluding the base is equal to a circle whose radius is a mean proportional between the side of the cone that is a generator and the radius of the circle which is the base of the cone. Now consider an isosceles cone, and again leave out the base. Look only at the curved surface that rises to the apex. This surface, like that of the cylinder, can be matched to a single circle, but here the radius of that circle is determined differently. It lies between two lengths of the cone, the slant side which is its generator, and the radius of its base. The radius of the circle is a mean proportional between these two. That is, it stands in the same ratio to the slant side as the slant side does to the base's radius. So the curved surface of the cone, though it narrows to a point, can still be gathered into a flat circle, its size set by the balance between the cone's slope and its base. Proposition 15. The surface of any isosceles cone has the same ratio to its base as the side of the cone has to the radius of the base. By Proposition 14, the surface of the cone is equal to a circle whose radius is a mean proportional between the side of the cone and the radius of the base. Hence, since circles are to one another as the squares of their radii, the proposition follows. Now compare the curved surface of an isosceles cone with its base. The claim is that these two areas stand in the same ratio as two of the cone's own lengths, the slant side of the cone and the radius of its base. This follows from the result just established. The surface of the cone is equal to a circle whose radius is a mean proportional between the slant side and the base's radius. And since circles are compared by the squares of their radii, the same proportion carries through here. So the surface of the cone has to its base the same ratio that the side of the cone has to the radius of the base. What matters is that the comparison of areas is reduced to a comparison of lengths. The larger geometric surface is brought back to something simpler and more measurable. Proposition 16. If an isosceles cone be cut by a plane parallel to the base, the portion of the surface of the cone between the parallel planes is equal to a circle whose radius is a mean proportional between 1, the portion of the side of the cone intercepted by the parallel planes, and 2, the line, which is equal to the sum of the radii of the circles in the parallel planes. Take an isosceles cone and slice it with a plane parallel to its base. This creates a smaller circle above, leaving a band of the cone's surface between the two parallel planes. Now focus on that band, the portion of the surface that lies between the two cuts. This curved surface can be matched to a single circle. The radius of that circle is determined by two lengths. One is the part of the cone's slant side that lies between the two planes. The other is a line equal to the sum of the radii of the two circular sections formed by the cuts. The radius of the circle is a mean proportional between these two. So even a portion of the cone's surface, taken between two slices, can be gathered into a single circle, its size set by how far the cut travels along the side and how wide the two circular edges are together. The lemmas are provided here. A lemma is a previously proven proposition that can help to prove another proposition. Cones having equal height have the same ratio as their bases, and those having equal bases have the same ratio as their heights. Consider two cones. If they have the same height, then their sizes are determined by their bases. The one with the larger base will be the larger cone, and the ratio between the cones will be the same as the ratio between their bases. On the other hand, if the two cones share the same base, then their sizes depend on their heights. The taller cone will be the larger, and the ratio between them will match the ratio of their heights. So a cone can be compared in two simple ways: by its base when the height is fixed, or by its height when the base is fixed. If a cylinder be cut by a plane parallel to the base, then as the cylinder is to the cylinder, so is the axis to the axis. Take a cylinder and slice it with a plane parallel to its base. This creates a smaller cylinder within the original, same shape, but shorter, sharing the same axis. Now compare the two cylinders. Their relationship does not depend on the base, since that remains the same. Instead, it follows the length of the axis, the height. So as one cylinder is to the other, so is its axis to the other's axis. The comparison reduces cleanly. When the base is unchanged, the size of the cylinder follows its height. 3. The cones which have the same bases as the cylinders and equal height are in the same ratio as the cylinders. Now take a cylinder and imagine a cone that shares the same base and the same height. Do this again with another pair, a second cylinder, and a cone that matches it in the same way. Now compare the two cylinders with each other and the two cones with each other. The relation holds steady. The cones stand to one another in the same ratio as the cylinders. So when base and height are aligned, the comparison does not change by moving from cylinder to cone. The shape changes, but the proportion remains the same. 4. Also, the bases of equal cones are reciprocally proportional to their heights, and those cones whose bases are reciprocally proportional to their heights are equal. Now consider cones that are equal in size. If one cone has a larger base, it must also have a smaller height. And if another has a smaller base, its height must be greater. The two vary against each other in such a way that the balance is preserved. So for equal cones, the bases and heights are inversely related. The larger one is, the smaller the other must be. And this works in reverse as well. If two cones are constructed so that their bases and heights stand in this same inverse relation, then the cones themselves will be equal. It's a kind of balance. What is gained in one dimension is lost in the other, and the whole remains unchanged. 5. Also the cones, the diameters of whose bases have the same ratio as their axes, are to one another in the triplicate ratio of the diameters of the bases. Now consider cones where the shape is scaled in a consistent way. If the diameter of the base and the height, the axis grow in the same ratio from one cone to another, then the cones remain similar in form. They stretch evenly in all directions. But their sizes do not increase in a simple, one-step way. When you compare such cones one to another, their volumes grow more rapidly. The relation between them follows what is called a triplicate ratio of the diameters. That is, the ratio is compounded 3 times over. So a small change in the diameter when carried through the whole shape becomes a much larger change in the cone itself. The form stays the same, but the size expands more quickly than it first appears. And all these propositions have been proved by earlier geometers. Proposition 17. If there he two isosceles cones, and the surface of one cone he equal to the base of the other, while the perpendicular from the center of the base of the first cone on the side of that cone is equal to the height of the second, the cones will be equal. Take two isosceles cones. In the first, look at its curved surface. In the second, look only at its base. Suppose these two are equal in area. Now, return to the first cone and draw a perpendicular from the center of its base to its slant side. Let that length be equal to the height of the second cone. With these two conditions in place, one matching areas, the other matching lengths, the two cones turn out to be equal. What seems like a comparison between different parts, a surface in one, a base in another, resolves into a balance of the whole. Proposition 18. Any solid rhombus consisting of isosceles cones is equal to the cone which has its base equal to the surface of one of the cones composing the rhombus, and its height equal to the perpendicular drawn from the apex of the second cone to one side of the first cone. Take a solid rhombus made from two isosceles cones joined at a common base, with their apexes pointing in opposite directions. Now focus on one of those cones and consider only its curved surface. Then look at the other cone, and from its apex imagine a perpendicular drawn to one side of the first cone. With these two parts, Archimedes forms a new cone, one whose base is equal to the surface of the first cone, and whose height is equal to that perpendicular from the apex of the second. The claim is that this new cone is equal to the whole solid rhombus. So the double figure, made from two cones joined together, can be matched by a single cone, provided its base and height are taken from the right parts of the original figure. Proposition 19. If an isosceles cone be cut by a plane parallel to the base, and on the resulting circular section, a cone he described having as its apex the center of the base of the first cone, and if the rhombus so formed be taken away from the whole cone, the part remaining will be equal to the cone with base equal to the surface of the portion of the first cone between the parallel planes, and with height equal to the perpendicular drawn from the center of the base of the first cone on one side of that cone. Take an isosceles cone and cut it with a plane parallel to its base. This creates a smaller circular section within the cone. On that circle, imagine building another cone, but this time its apex is not above it, but at the center of the original base, so it points inward toward the middle of the first cone. Now, together with the portion of the original cone below the cut, this forms a solid rhombus inside the larger cone. Remove that rhombus. What remains is not irregular or undefined. It can be matched to a single cone. This new cone has its base equal to the curved surface of the band of the original cone between the two parallel planes, and its height is equal to the perpendicular drawn from the center of the original base to one side of the cone. So even after cutting and removing a part, what is left can still be gathered into a simpler form, again, a cone, built from the right pieces of the original figure. Proposition 20. If one of the two isosceles cones forming a rhombus be cut by a plane parallel to the base, and on the resulting circular section a cone be described having the same apex as the second cone, and if the resulting rhombus be taken from the whole rhombus, the remainder will be equal to the cone with base equal to the surface of the portion of the cone between the parallel planes, and with height equal to the perpendicular drawn from the apex of the second cone to the side of the first cone. Begin with a solid rhombus formed by two isosceles cones joined at a common base, their apexes pointing in opposite directions. Now take one of these cones and cut it with a plane parallel to its base, creating a smaller circular section. On that circle, construct another cone, but this time let it share the same apex as the second cone of the rhombus. In this way, a smaller rhombus is formed within the larger one. Remove this smaller rhombus. What remains can again be matched to a single cone. This cone has its base equal to the curved surface of the portion of the first cone between the two parallel planes, and its height is equal to the perpendicular drawn from the apex of the second cone to the side of the first cone. So even within this more layered construction, the same pattern holds. Parts are removed, but what remains can still be gathered into a single balanced figure. Proposition 21. A regular polygon of an even number of sides is inscribed in a circle, so that a line joining two opposite vertices is a diameter. If two vertices with one vertex between them are joined, and the other lines parallel to that one are drawn by joining corresponding pairs of vertices, then a set of parallel chords is formed inside the polygon in such a way that the sum of all those parallel chords compared with the diameter has the same ratio as the side of the polygon next to one end of that diameter. Imagine a circle, and inside it, a regular polygon with an even number of sides, balanced so that a straight line joining two opposite corners passes through the center and becomes a diameter. Now begin from one end of that diameter. Join two vertices of the polygon, skipping one in between. Then, across the shape, draw other lines parallel to this one, each connecting matching pairs of vertices. What you get is a set of evenly spaced parallel chords running across the polygon. Now take all these chords together and compare their total length with the diameter. The relation is not arbitrary. The sum of these parallel chords stands to the diameter in the same ratio as one side of the polygon, the side next to one end of the diameter. So a pattern emerges from within the symmetry. Lines drawn across the figure, when gathered together, reflect the proportion already present at its edge. Proposition 22. A polygon is inscribed in a segment of a circle so that all its sides, except the base, are equal, and the number of those sides is even, with the topmost point lying at the middle of the segment. If lines are drawn parallel to the base, each joining corresponding pairs of vertices, then a series of parallel chords is formed within the figure, in such a way that the sum of these parallel chords, together with the final segment reaching the base, when compared to the line from the midpoint to the base, has the same ratio as the line from the top point to one adjacent vertex, compared to the side next to it. Now imagine not a full circle, but a segment of one, a curved shape bounded by an arc above and a straight line below. Inside this segment, place a polygon. Its base lies along the straight edge, while all its other sides are equal, rising symmetrically to a single top point at the middle of the arc. The number of these equal sides is even, so the figure remains balanced. Now draw lines across the shape, each one parallel to the base, joining matching pairs of vertices on either side. This creates a series of parallel chords, stepping down from the top toward the base. If you take all these chords together and include the final segment that reaches the base, and compare their total with the straight line drawn from the midpoint down to the base, a proportion appears. This total stands to that central line in the same ratio as the line from the top point to one of its neighboring vertices stands to the side next to it. So once again, lines drawn within the figure, when taken together, reflect a proportion already present in a single part of it. Proposition 23. Take a great circle of a sphere and inscribe within it a regular polygon whose number of sides is divisible by 4. Then draw two diameters of the circle at right angles to one another, each passing through opposite vertices of the polygon. These diameters divide the figure in a symmetrical way, setting up the structure for the relationships that follow between the sides and the lines drawn through the polygon. Therefore, according to assumption 4, the surface of the hemisphere is greater than that of the inscribed figure, and the same is true of the other halves of the figures. Hence, the surface of the sphere is greater than the surface described by the revolution of the polygon inscribed in the great circle about the diameter of the great circle. Take a sphere and imagine one of its greatest circles, the largest circle that can be drawn across its surface. Within this circle, inscribe a regular polygon whose number of sides is divisible by 4 so that it can be divided evenly. Now draw 2 diameters at right angles to one another, each passing through opposite vertices of the polygon. These lines divide the figure into equal parts, giving it a clear symmetry. Now imagine revolving this polygon around one of those diameters. As it turns, it traces out a surface within the sphere. But this surface does not reach as far as the sphere itself. From what has already been established, the curved surface of the sphere, already seen to exceed any inscribed figure, remains greater than the surface formed by this rotation, and the same holds when each half is considered. So even when the polygon is extended into a solid by rotation, it still falls short. The sphere surrounds it, just as the circle surrounds its inscribed shapes. Proposition 24. A regular polygon, whose number of sides is a multiple of 4, is inscribed in a great circle of a sphere with a diameter passing through 2 opposite vertices. If a line is drawn joining 2 vertices that span 2 sides, and all other lines parallel to it are drawn joining corresponding pairs of vertices, a system of parallel chords is formed across the polygon. When this polygon is rotated about that diameter, it generates a surface made up of parts of cones, and the total surface is equal to that of a circle whose radius is determined by the product of one side of the polygon and the sum of those parallel chords. Take a sphere and again begin with one of its great circles. Inside this circle, inscribe a regular polygon whose number of sides is a multiple of 4, so it divides evenly. Let a diameter pass through 2 opposite vertices. Now draw a line across the polygon, joining 2 vertices that skip one in between. Then draw all other lines parallel to it, each connecting matching pairs of vertices. This creates a set of parallel chords running across the figure. Now imagine rotating this polygon around the diameter. As it turns, each side sweeps out a surface. These surfaces are not arbitrary. They form parts of cones joined together around the axis of rotation. If you take all these surfaces together, their total can be matched to a single circle. The radius of that circle is determined by 2 things, one side of the polygon and the sum of all those parallel chords drawn across it. So once again, a more complex surface, built from many moving parts, can be gathered into a single balanced figure. Proposition 25. The surface of the figure, inscribed in a sphere as in the last propositions, consisting of portions of conical surfaces, is less than 4 times the greatest circle in the sphere. Consider the figure formed inside a sphere from the previous construction, built from many small surfaces, each coming from the rotation of the polygon's sides. Though this figure wraps around and follows the shape of the sphere, it does not fully match it. Its surface, made up of these conical parts, remains less than 4 times the area of the greatest circle of the sphere. So even when many pieces are combined and carried around the sphere, the whole still falls short of a simple measure taken from the sphere itself. Proposition 26. The figure inscribed as above in a sphere is equal in volume to a cone whose base is a circle equal to the surface of the figure inscribed in the sphere, and whose height is equal to the perpendicular drawn from the center of the sphere to one side of the polygon. Now take the figure inscribed in the sphere from the earlier construction, the one formed by revolving the polygon, so that its surface is made up of portions of cones. This figure, though enclosed within the sphere, is still a solid in its own right. And Archimedes shows that its volume can be matched exactly by a single cone. The base of that cone is taken to be equal to the surface of the inscribed figure. Its height is the perpendicular drawn from the center of the sphere to one side of the polygon from which the figure was generated. So the whole solid, built from many conical parts, is gathered into one cone, its size determined by the surface it presents and by a single inward distance from the center. Proposition 27. The figure inscribed in the sphere as before is less than 4 times the cone whose base is equal to a great circle of the sphere, and whose height is equal to the radius of the sphere. Now consider the same inscribed figure within the sphere. Archimedes compares its volume to a simpler solid, a cone whose base is equal to a great circle of the sphere, and whose height is equal to the sphere's radius. The claim is that the inscribed figure is less than 4 times this cone. So even though the figure is built to follow the sphere from within, its volume still remains below a clear limit, set by a cone drawn from the sphere's own most basic measures, its greatest circle and its radius. Proposition 28. Let a regular polygon, whose number of sides is a multiple of 4, be drawn around a great circle of a sphere so that each of its sides touches the circle. Then draw another circle around this polygon, sharing the same center as the sphere's great circle. If a line is drawn through 2 opposite vertices of the polygon so that it divides the figure into equal parts, and this line passes through the sphere, it meets the surface of the sphere at a point along that line. Now begin again with a great circle of a sphere. Around this circle, draw a regular polygon so that each of its sides just touches the circle from the outside. Then around this polygon, draw another circle, sharing the same center as the original great circle. Now take a line passing through 2 opposite vertices of the polygon, dividing it into 2 equal parts. Let this line extend through the sphere itself. As it passes through, it meets the surface of the sphere at a point along its length. So the construction begins to move outward, from the circle to the polygon around it, and then back inward again, as a single line cuts through and reconnects with the sphere. Proposition 29. In a figure drawn around a sphere in the same way as before, so that it surrounds the sphere and touches it along its sides, lines are taken across the figure, joining pairs of vertices in a consistent, parallel pattern in such a way that the total surface of this surrounding figure is equal to that of a circle whose radius is determined by the product of one side of the polygon and the sum of those parallel lines drawn across it. Now take a figure drawn around a sphere, enclosing it on all sides so that its faces touch the sphere from the outside. Across this figure, draw lines joining pairs of vertices, keeping them parallel and arranged in a regular pattern, much like before. These lines cut across the figure in a consistent way, creating a set of parallel sections. If all these are taken together, the total surface of the surrounding figure can be matched to a single circle. The radius of that circle is determined by 2 parts, one side of the polygon, and the sum of all the parallel lines drawn across it. So even a surface built around the sphere, made from many faces, can be gathered into one figure, its size fixed by the same kind of relation seen before. Proposition 30. The surface of a figure circumscribed as before about a sphere is greater than 4 times the great circle of the sphere. Now consider the figure drawn around the sphere from before, the one that encloses it touching along its sides. This outer figure follows the shape of the sphere, but always from the outside. Its faces do not curve, they stretch across, standing slightly away from the surface. Because of this, its total surface is not the same as that of the sphere. It is greater. More precisely, the surface of this circumscribed figure exceeds 4 times the area of the greatest circle of the sphere. So the same pattern appears again. From within, the constructed figure falls short. From without, it goes beyond, and the sphere itself remains between these 2 bounds. The translator notes that this is one of the most famous results of this book. It is used every day to find the surface area of a sphere. In that way, this equation is relevant from someone taking geometry in a high school to someone doing something complex like space science. In mathematical terms, it says the area of a sphere is equal to 4 times pi times the radius squared. This also led him to find the surface area of a cylinder and a cone. Proposition 31. The solid of revolution circumscribed as before about a sphere is equal to a cone whose base is equal to the surface of the solid and whose height is equal to the radius of the sphere. The solid is, as before, a solid inscribed in a larger sphere, and, since the perpendicular on any side of the revolving polygon is equal to the radius of the inner sphere, the proposition is identical with Proposition 26. Now consider the solid formed by revolving the outer figure around the sphere, the one that surrounds it from the outside. This solid, though more complex in shape, can again be matched to something simpler. It is equal to a single cone. The base of that cone is taken to be equal to the entire surface of the solid, and its height is equal to the radius of the sphere. This follows the same pattern seen earlier. Each part of the revolving figure keeps a constant distance from the center, equal to the sphere's radius. Because of this, the whole solid gathers into a cone in exactly the same way as before. So even here, nothing new is introduced, only the same idea, seen again from the outside instead of within. Proposition 32. A regular polygon with a number of sides divisible by 4 is inscribed in a great circle of a sphere, and a similar polygon is drawn around the same circle. Each polygon is then rotated about a diameter through opposite vertices, forming one solid inside the sphere, and another enclosing it in such a way that the surface of the outer figure, compared to the inner one, follows the square of the ratio of their sides, while the volumes of the two figures follow the cube of that same ratio. This extends to 1. The surfaces of the circumscribed and inscribed figures are to one another in the duplicate ratio of their sides, and 2. The figures themselves, that is their volumes, are in the triplicate ratio of their sides. Begin again with a great circle of a sphere. Inside it, place a regular polygon. Around it, draw another similar polygon, touching the circle from the outside. Both have the same number of sides, and that number is divisible by 4, so the figure remains balanced. Now imagine each of these polygons being rotated about a diameter passing through opposite vertices. The inner polygon forms a solid within the sphere. The outer polygon forms a solid that surrounds it. Now compare the two. The surfaces of these solids do not grow in a simple one-step way. Instead, they follow the square of the ratio of their sides. If one polygon has sides twice as long as the other, its surface becomes 4 times as great. The volumes grow even faster. They follow the cube of that same ratio. If the sides are doubled, the volume becomes 8 times as great. So from the same construction, 2 patterns appear. The surfaces increase with the square of the sides. The solids themselves increase with the cube. It is a shift from length to surface to volume, each step expanding the comparison further, but always tied back to the same simple measure, the side of the polygon. Proposition 33. The surface of any sphere is equal to 4 times the greatest circle in it. Now at last, return to the sphere itself. All along, figures have been drawn inside it and around it, some falling short, others extending beyond. But each of them has been measured against the same thing, the greatest circle of the sphere. Here that comparison becomes exact. The entire surface of the sphere is equal to 4 times the area of its greatest circle. So the curved surface, which seemed at first difficult to grasp, resolves into something simple. Not a new figure, but a familiar one, repeated 4 times. And in that, the sphere is finally measured. Proposition 34. Any sphere is equal to 4 times the cone, which has its base equal to the greatest circle in the sphere, and its height equal to the radius of the sphere. For the cylinder is 3 times the cone, with the same base and height as proved by Euclid, which is 6 times the cone with the same base, and with height equal to the radius of the sphere. In this case, the height is equal to the diameter of the base, and therefore the circle is that whose radius is the diameter of the sphere, or a circle equal to 4 times the great circle of the sphere. Therefore the surface of the cylinder with the bases is equal to 6 times the great circle. Now Archimedes turns from the surface of the sphere to the sphere as a solid. He says that any sphere is equal to 4 times a cone whose base is the greatest circle of the sphere and whose height is the radius. This is a striking result because it gathers the whole sphere into a figure much simpler than itself. Instead of trying to measure the sphere directly, Archimedes compares it to a cone built from the sphere's own most basic parts, its largest circle, and the distance from its center to its surface. The reasoning passes through the cylinder. A cylinder with the same base and height as 2 such cones is 3 times 1 cone by Euclid's result. And since the height of that cylinder is equal to the diameter of the sphere, that is, twice the radius, it follows that the cylinder can be understood in terms of 6 cones of the same base and radius. Now the circle determined by that diameter is not just any circle. Its radius is the diameter of the sphere, which makes its area 4 times the area of the sphere's greatest circle. From this, the full surface of the cylinder, together with its 2 bases, comes out to 6 times the great circle. So once again, the sphere is approached through figures around it, and what first seems too round, too continuous to measure, is brought back to a simple proportion. The whole sphere is equal to 4 such cones. The translator notes that this is one of the most famous results of this book. It is used every day to find the volume of a sphere. In mathematical terms, it says the volume of a sphere is equal to 4 over 3 times pi times the radius cubed. This also led Archimedes to find the volume of a cylinder and a cone. Proposition 35. A polygon is inscribed in a segment of a circle, with one side forming the base of the segment and all the remaining sides equal in length, their number being even, and the highest point lying at the middle of the arc. When this polygon is rotated about the line from that highest point to the base, it generates a solid figure contained within a segment of a sphere in such a way that the surface of this solid is equal to that of a circle whose radius is determined by the product of one side of the polygon and the sum of the parallel segments drawn across it, including the final segment at the base. Now return to a segment of a circle, a shape bounded by an arc above and a straight line below. Inside this segment, a polygon is inscribed. Its base lies along the straight edge, while all the other sides are equal, rising evenly toward a highest point placed at the middle of the arc. Because the number of those equal sides is even, the figure remains balanced from one side to the other. Now imagine this polygon revolving around the straight line drawn from that highest point down to the base. As it turns, it generates a solid figure inside a segment of a sphere. The surface of this solid, though formed from many moving sides, can be matched to a single circle. The radius of that circle is determined by 2 things taken together, one side of the polygon and the sum of the parallel segments drawn across the figure, including the final one at the base. So once again, a surface built from rotation and many separate parts is gathered into one simple figure, a circle whose size is fixed by the structure of the original polygon. Proposition 36. The surface of the figure inscribed as before in the segment of a sphere is less than that of the segment. This is clear because the circular base of the segment is a common boundary of each of 2 surfaces, of which one, the segment, includes the other, the solid, while both are concave in the same direction according to assumption 4. Now take the solid figure inscribed within the segment of the sphere from the previous construction. Its surface lies inside the surface of the spherical segment, and both share the same circular base. They bend in the same direction, and one is contained within the other. Because of this, the comparison is already settled. The surface of the inscribed figure is less than the surface of the segment of the sphere. So here the result follows directly from the shape itself. With the same boundary, and with one surface lying wholly within the other, the inner one must be the lesser. Proposition 37. The surface of the solid formed by revolving the inscribed polygon in the spherical segment about the diameter is less than the surface of a circle whose radius is the line from the midpoint of the arc to one end of it. Now consider the solid formed by revolving the inscribed polygon within the spherical segment about its diameter. This solid lies within the segment, and so its surface remains less than the surface that bounds the segment itself. And that bounding surface, in turn, is measured by a circle whose radius is the straight line drawn from the midpoint of the arc to one end of it. So the surface of the revolving solid is less than the surface of that circle. The figure comes close by rotation, but it still remains within the segment, and for that reason its surface stays below the measure set by the arc itself. Proposition 38. The solid figure described as before in a segment of a sphere less than a hemisphere, together with the cone whose base is the base of the segment and whose apex is the center of the sphere, is equal to a cone whose base is equal to the surface of the inscribed solid and whose height is equal to the perpendicular from the center of the sphere on any side of the polygon. Now take the solid figure formed inside a spherical segment that is smaller than a hemisphere. To this figure, add a cone whose base is the base of the segment and whose apex is at the center of the sphere. The result, Archimedes says, is equal to a single cone. The base of this cone is equal to the surface of the inscribed solid, and its height is the perpendicular drawn from the center of the sphere to any side of the polygon from which the solid was formed. So the figure inside the segment is not measured alone. It is first completed by adding a cone from the center, and only then does the whole become equal to one simpler cone, determined by the surface of the solid and a single inward distance from the sphere's center. Proposition 39. Let a segment of a great circle of a sphere, smaller than a semicircle, be taken, and let the center of the sphere be joined to the two ends of the segment. Around the sector formed in this way, let a polygon be circumscribed so that, apart from the two radii, its remaining sides are even in number and all equal, with a line from the center to the midpoint of the arc bisecting the segment. The circle circumscribing this polygon will have the same center as the given great circle. Now take a segment of a great circle smaller than a semicircle and join its two endpoints to the center of the sphere. This gives a sector, bounded by two radii and the arc between them. Around this sector, draw a polygon. The two radii remain as part of the boundary, while the remaining sides are equal in length and even in number, arranged symmetrically on either side. The line from the center to the midpoint of the arc divides the whole figure into two equal parts. And because the construction is balanced in this way, the circle drawn around the polygon shares the same center as the original great circle. So even though the polygon is drawn around only a part of the circle, the symmetry of the construction keeps everything anchored to the same center. Proposition 40. The surface of the figure circumscribed about the sector in the same way as before is greater than the surface of a circle whose radius is equal to the line from the midpoint of the arc to one end of it. Now return to the sector and the figure drawn around it. This outer figure does not follow the curve closely. It stands outside it, touching along its sides, but never bending with it. When this figure is considered as a whole, its surface extends beyond the surface that would be formed by the arc itself. More precisely, it is greater than the surface of a circle whose radius is the straight line drawn from the midpoint of the arc to one of its ends. So once again, the pattern holds. The figure drawn outside does not just enclose, it exceeds, setting a clear upper bound beyond the curve it surrounds. Proposition 41. Let a segment of a great circle of a sphere, smaller than a semicircle, be taken, and within the sector formed by joining its endpoints to the center, let a polygon be inscribed whose equal sides are even in number. Around this, let a similar polygon be circumscribed, with each of its sides parallel to the corresponding side of the inner polygon, and let the outer polygon be enclosed by its circumscribing circle. If these figures are revolved together about the radius that bisects the segment, they generate an inner and an outer solid. The proposition says that the surfaces of these two solids are in the ratio of the square on the side of the outer polygon to the square on the side of the inner one, and that their volumes, together with the corresponding cones, having the same bases, and their vertices at the axis, are in that same ratio. Take again a segment of a great circle, smaller than a semicircle, and form the sector by joining its ends to the center. Within this sector, inscribe a polygon with equal sides, even in number. Around it, draw another polygon of the same form, each of its sides parallel to the corresponding side of the inner one. Then enclose this outer polygon with its own circle. Now let all of this revolve about the radius that bisects the segment. As it turns, two solids are formed, one from the inner polygon and one from the outer. Now compare them. The surfaces of these two solids do not grow in a simple proportion. They follow the square of the ratio of the sides of the polygons. If one polygon has sides in a certain ratio to the other, the surfaces of the solids follow the square of that ratio. And if you include the cones formed with the same bases and with their vertices on the axis, then the volumes follow that same proportion. So once again, the same pattern appears. From lines to surfaces and from surfaces to solids, the relation deepens, but it always traces back to the sides of the original polygons. Proposition 42. Let a segment of a sphere, smaller than a hemisphere, be taken, with the radius drawn from the center perpendicular to its base. The proposition says that the surface of this segment is equal to that of a circle whose radius is the line from the midpoint of the arc to one end of the segment. Take a segment of a sphere, smaller than a hemisphere. From the center of the sphere, draw a straight line down to the base of the segment, meeting it at a right angle. Now look at the curved surface of this segment. Archimedes shows that this surface can be matched exactly to a single circle. The radius of that circle is the straight line drawn from the midpoint of the arc of the segment to one of its ends. So the curved surface of the segment, though part of a sphere, resolves into a circle, its size fixed by a single line taken across the arc itself. Proposition 43. Let a segment of a sphere be taken, even if it is greater than a hemisphere, with the same line drawn from the midpoint of the arc to one end of the segment. The proposition says that the surface of this segment is still equal to that of a circle whose radius is that same line. Now take a segment of a sphere again, but this time allow it to be larger, even greater than a hemisphere. Draw the same line as before, from the midpoint of the arc down to one of its ends. Now consider the curved surface of this larger segment. Even here, the same relation holds. The surface of the segment is equal to that of a circle whose radius is that same line. So whether the segment is small or extends beyond a hemisphere, the measure does not change. The surface always returns to that one line, drawn across the arc, fixing the size of the circle that equals it. Proposition 44. The volume of any sector of a sphere is equal to a cone whose base is equal to the surface of the segment of the sphere included in the sector, and whose height is equal to the radius of the sphere. Now consider a sector of a sphere, a portion cut out by taking a segment of the sphere and joining it to the center. Focus on the whole solid, not just its surface. Archimedes shows that this volume can be matched to a single cone. The base of that cone is equal to the curved surface of the spherical segment contained within the sector, and its height is equal to the radius of the sphere. So the solid, shaped by the curve of the sphere and gathered toward its center, is measured by a cone built from those same parts, the surface it presents, and the distance back to the center. Book 2. Archimedes to Dositheus greeting. On a former occasion, you asked me to write out the proofs of the problems, the enunciations of which I had myself sent to Conon. In point of fact, they depend for the most part on the theorems of which I have already sent you the demonstrations, namely, 1. That the surface of any sphere is 4 times the greatest circle in the sphere. 2. That the surface of any segment of a sphere is equal to a circle whose radius is equal to the straight line drawn from the vertex of the segment to the circumference of its base. 3. That the cylinder whose base is the greatest circle in any sphere, and whose height is equal to the diameter of the sphere, is itself in magnitude half as large again as the sphere, while its surface, including the 2 bases, is half as large again as the surface of the sphere. And 4. That any solid sector is equal to a cone whose base is the circle which is equal to the surface of the segment of the sphere included in the sector, and whose height is equal to the radius of the sphere. Such then of the theorems and problems as depend on these theorems I have written out in the book which I send herewith. Those which are discovered by means of a different sort of investigation, those namely which relate to spirals and the conoids, I will endeavor to send you soon. Proposition 1, which is a problem. Given a cone or a cylinder, to find a sphere equal to the cone or to the cylinder. Now the direction changes. A cone or a cylinder is given, and the task is to find a sphere equal to it. To approach this, you begin by asking, what determines the size of each figure? For the cone or the cylinder, it comes down to the base and the height. For the sphere, its size is already known to relate to a cone whose base is its greatest circle and whose height is its radius. So the way forward is to take the given solid and express it in those same terms, reduce it to something that can be compared with a cone. Once that is done, the problem becomes clearer. Find a radius such that a sphere built from it would produce a cone equal to the one already obtained. So the construction is guided by this idea. First, bring the given figure into a form the sphere already understands, and then choose the sphere so that both agree. Proposition 2. Let a segment of a sphere be taken, with a diameter drawn across its base, and the center of the sphere identified. Then let another diameter of the sphere pass through the center and bisect that base, meeting it at its midpoint in such a way that the volume of the segment is equal to that of a cone having the same base, with its height determined by a relation involving the radius of the sphere and the parts into which that diameter is divided. Take a segment of a sphere and look first at its base, the circle that cuts it off from the rest of the sphere. Draw a diameter across that base. Then, through the center of the sphere, draw another diameter in such a way that it passes through the midpoint of the base and stands across the figure as its central line. Now the solid is laid out in a way that can be measured. The aim is to compare the segment with a cone built on the same base. The base remains unchanged, so the question is no longer about width, but about height. What height must the cone have in order to be equal in volume to the spherical segment? Archimedes shows that this height is not chosen at random. It is determined by the radius of the sphere together with the parts into which the central diameter is divided by the base of the segment. So the problem is set up by drawing the right lines first. Once the sphere's center, the base, and the divided diameter are all in view, the segment can be related to a cone standing on the same circle. Proposition 3. Which is a problem. To cut a given sphere by a plane so that the surfaces of the segments may have to one another a given ratio. Now the task is not to compare a sphere with another figure, but to divide the sphere itself. A sphere is given, and the aim is to cut it with a plane so that the surfaces of the two resulting segments stand to one another in a given ratio. To approach this, the first thing to notice is that the surface of a spherical segment is not treated here as something mysterious or separate. Earlier results have already shown that the surface of a segment can be matched to a circle determined by a line drawn from the arc. So the problem becomes one of position. You imagine moving the cutting plane up or down through the sphere. Each new cut changes the two segments at once. One grows, the other shrinks. And as that happens, their surfaces change with it. The question is therefore not simply where to cut, but where to place the plane so that the two curved surfaces come into exactly the required proportion. So the way into the problem is this. First, translate each segment's surface into something measurable, then shift the plane until the two measures answer to the given ratio. What looks like a problem about cutting a solid is really a problem about finding the right balance point within it. Proposition 4, which is a problem. To cut a given sphere by a plane so that the volumes of the segments are to one another in a given ratio. Here the problem goes a step further. A sphere is given and it must be cut by a plane so that the two parts left behind are not equal, but stand to one another in a ratio that has already been assigned. But this time the comparison is not between surfaces. It is between the solids themselves. So the way to think about it is not by looking only at the cut, but by imagining how the whole volume shifts as the plane moves. Raise the plane, and one segment shrinks while the other grows. Lower it, and the relation changes again. The task is to find the one position where this changing division of the sphere produces exactly the required ratio of volumes. So the approach is to treat the plane as something adjustable. You move it through the sphere, knowing that each new position gives a new pair of segments, until the two solids stand to one another as required. What is being sought, then, is not just a cut, but the precise place of the cut, the one point where the sphere divides into the right proportion. Proposition 5, which is a problem. To construct a segment of a sphere similar to one segment and equal in volume to another. Now the task becomes more delicate. Two segments of a sphere are given, and from them a new one must be produced, one that is similar to the first but equal in volume to the second. So the construction has to satisfy two demands at once. To be similar to the first segment means its shape must be preserved. The curve must rise in the same way, and the relation between its height and its base must remain the same. In other words, it cannot simply be made wider or narrower at random. It has to keep the same form. But at the same time, its volume must match that of another segment altogether. So the way to approach the problem is to begin with the segment whose shape is to be copied. That segment gives the pattern. It tells you what proportion must be kept between the base, the height, and the sphere from which the segment is taken. Then you turn to the other segment, the one whose volume is to be matched. That gives the size the new figure must ultimately have. The work, then, is to scale the first segment without changing its form until its volume becomes equal to the second. So this is really a problem of controlled enlargement or reduction. One segment provides the shape, the other provides the measure, and the construction must bring the two together in a single figure. Proposition 6, which is a problem. Given two segments of spheres, to find a third segment of a sphere similar to one of the given segments and having its surface equal to that of the other. Now the task is split across two different segments. From one of them, you must keep the shape. From the other, you must take the surface. The segment to be constructed must be similar to the first, so its proportions cannot change. Its curve, its height, and the relation of its parts must follow the same pattern, but its surface must be equal to that of the second segment. So the problem is to adjust the size without altering the form. The natural way to approach it is to begin with the segment whose shape is to be preserved. That segment gives the rule of construction. It tells you what kind of segment the new one must be. Then you turn to the other segment, not for its shape, but for its measure. Its surface gives the quantity the new figure must match. The work, then, is to enlarge or reduce the first kind of segment until its surface becomes equal to that of the second. So one segment supplies the form, and the other supplies the measure. The problem is to bring those two together in a single spherical segment. Proposition 7, which is a problem. From a given sphere to cut off a segment by a plane so that the segment may have a given ratio to the cone which has the same base as the segment and equal height. Now the problem brings together two things that are already closely linked: a spherical segment and the cone that stands on the same base and rises to the same height. A sphere is given, and from it a segment must be cut off by a plane. But not just any segment. It must be one whose volume stands to that cone in a given ratio. So the first thing to notice is that the cone is not an added figure from elsewhere. It is built directly from the segment itself. Once the cutting plane is chosen, the base is fixed, the height is fixed, and with them the cone is fixed as well. That means everything depends on the position of the plane. Move the plane closer to the top of the sphere, and the segment becomes smaller. Its base narrows, its height shortens, and the cone changes with it. Move the plane deeper, and both grow again, but not in the same way. The segment and the cone remain tied to the same base and height, yet the relation between their volumes shifts as the cut changes. So the way to approach the problem is to think of the plane as moving through the sphere until the segment it leaves behind bears the required proportion to its cone. The construction is guided by that changing balance. Not just the size of the segment, not just the size of the cone, but the ratio between the two, as both are determined by the same cut. Proposition 8. Let a sphere be cut by a plane that does not pass through its center, forming two segments, one larger and one smaller. The proposition begins by comparing these two segments, setting up a relation between them that depends on how the cutting plane divides the sphere. Now let a sphere be cut by a plane that does not pass through its center. The cut produces two unequal segments, one larger, one smaller. Both belong to the same sphere, and both are determined by the same circular base where the plane passes through. To approach the relation between them, the important thing is not only that one is greater and the other less, but that they are connected by a single cut. Move the plane upward or downward, and both change together. One gains what the other loses. So the comparison begins by fixing attention on that shared division. The plane does not create two unrelated figures. It creates two parts whose sizes depend on the same radius, the same center, and the same distance of the cut from that center. Once those are in view, the relation between the larger segment and the smaller one can be expressed through the way the sphere has been divided. What matters here is that the two segments are not compared from the outside, but as complementary parts of one whole. Proposition 9. Of all segments of spheres which have equal surfaces, the hemisphere is the greatest in volume. Now consider all segments of spheres that have the same surface. At first, they may seem quite different. Some are shallow, spreading wide but not rising much. Others are steep, rising higher but covering less of the sphere. Yet if their surfaces are equal, they are all being measured by the same amount of curved area. Among all such segments, one stands apart. The hemisphere, the segment that cuts the sphere exactly in half, has the greatest volume. So even when the surface is fixed, the volume is not. And of all the possible ways to shape that surface into a segment, the most balanced one, the hemisphere, encloses the most. Our audiobook ends here. Thank you for listening. If you want any particular book in this channel, please let us know in the comments.